Welcome back to the Deep Dive. Today, we are putting on our architect hats because we're not just looking at security tools. We are examining the blueprints. We are taking a really comprehensive deep dive into CISSP Domain-3. Security architecture and engineering.
Yeah, this is a big one. It's what, 13% of the exam weight? But honestly, more importantly, it represents this fundamental shift in how we think about protection.
How so?
Well, it's where you stop thinking about security as just, a feature you install right at the end, maybe slap on a firewall or something.
Right. Bolting it on.
Exactly.
Yeah.
Instead, you start seeing security as an emergent property of the system itself. It grows out of the design.
That really is the core idea, isn't it? You can't truly secure a fundamentally poorly designed system. So our mission today, for you listening, is to give you a structured path through this, well, pretty dense domain.
We'll move from these sometimes abstract concepts of trust and the formal security models all the way down to the very concrete engineering needed.
Building and securing everything from, say, software in the cloud down to the physical walls of the data center itself. It's a broad scope.
It really is.
Okay, so let's start with those theoretical frameworks. These are the fundamental rules, the kind of traffic laws for handling information, formal models that dictate how assets get accessed.
Yeah, and if we really want systems that are provably secure or at least demonstrably trustworthy, we need these kinds of rigid rules as a foundation.
Makes sense. So where do we begin? Maybe with models focused on integrity? That's all about making sure data is accurate, reliable, not tampered with.
Good place to start. The first major one here is Biba, the Biba integrity model. It originally came about partly as a kind of mirror image of the military confidentiality models like Bell-LaPadula, but flipped to focus entirely on preventing unauthorized data modification.
Okay, so it's obsessed with data purity, keeping things accurate.
That's a great way to put it, data purity. And it enforces this with two really strict axioms or rules. The simple integrity axiom is often stated as no read down.
Right, no read down. Now, why is that such a key rule? It feels a bit counterintuitive. If I have high integrity clearance, why can't I read data that's considered less trusted?
Because the moment you read data from a lower integrity level data that maybe hasn't been properly vetted or cleansed or validated, you risk contaminating your own higher integrity data or processes.
So it's like bringing mud into a clean room.
Exactly like that. It's a defense mechanism against pollution, essentially. If you ingest untrusted input, whatever output you produce, even if your high-level process follows all the rules, it's potentially compromised now. Biba aims to just shut down that risk entirely.
Okay, that makes sense. And the counter rule, the flip side, is the star integrity axiom.
Oh.
No write-up. You can't write data to an object that sits at a higher integrity level than you.
Right. And this stops low security, potentially corrupt, maybe just plain wrong information from flowing upwards and overwriting critical high-level data. So together, those two axioms, no read down, no write-up, ensure the information flow is strictly controlled to maintain the purity of your most critical assets.
It's very hierarchical, very strict.
Very. Now, contrast that with the Clark-Wilson integrity model. This one feels much more grounded in the commercial world. Think banking systems, financial transactions, inventory control.
Yeah, things where data needs to change, but in a controlled way.
Precisely. Clark-Wilson focuses less on those military-style hierarchical data levels and more on transactional integrity and, crucially, accountability. It recognizes that in business, data has to be modified, but it must change reliably, ethically, and traceably.
So how does it enforce that?
Through strict adherence to procedures and a core concept, separation of duties. Its key elements are constrained data items, CDIs. That's the data you need to protect, like, say, an account balance.
Okay, the critical data element.
Yep. And then you have transformation procedures, TPs. These are the only allowed mechanisms, the specific programmed functions that can manipulate those CDIs.
So if the account balance is the CDI, the TP might be the transfer funds function or the deposit check function?
Exactly. The TP is that validated, approved, abstract operation. This ensures every change is checked, properly formatted, authorized. It's not just some admin randomly changing a value in the database.
And Clark-Wilson goes further, right? It brings in auditing.
It does. It requires integrity verification procedures, IVPs. These are essentially audits or scans that run against the data items to confirm they still meet predefined integrity constraints. They might check for internal consistency or compliance with business rules.
So it's constantly checking itself.
Yeah, and it's highly auditable because those TPs inherently require a clear clear separation of duty between who defines the procedure and who executes it, and the IVPs provide the verification loop. Very commercially focused.
Okay, that covers integrity pretty well.
Yeah.
Let's shift gears to confidentiality models.
Yep.
Now we're focused on restricting access, preventing secrets from leaking out.
Right, and confidentiality models often have to deal with some pretty sophisticated attack vectors, not just direct, can I read this file stuff, but things like covert channels.
Oh, covert channels. Always a tricky concept. Let's clarify that. What exactly is a covert channel in this context?
So a covert channel is basically a communication path that the system designer never intended to exist. It's sneaking information out through the back door, often using shared resources.
Like how? Give us an example.
Okay, imagine you have a high-security process, maybe handling top-secret data, and a low-security process running on the same machine. They might share a physical resource, maybe the hard drive's read-write head, or even just CPU timing.
Okay.
The high-security process, wanting to leak a secret 1 or 0 bit, could subtly manipulate the timing of its disk access. Maybe it forces a long delay for a 1 and does a quick access for a 0.
And the low security process.
Just sits there measuring those timing variations. It can decode the pattern. It's not reading the secret data directly, but it's receiving information about it through this unintended channel.
That's clever and sneaky.
Very. So a non-interference model is specifically designed to try and prevent this. It aims to ensure that actions performed at one security level, the high level, cannot alter the state or be observed or understood by another lower level in any way that leaks information. It's about preventing that subtle influence.
That sounds incredibly difficult to implement perfectly.
Oh, it is, especially in complex systems. Then, more practically, when we talk about restricting what a specific piece of software or a process can actually do, we often use confinement, which you might know better as sandboxing.
Right, sandboxing.
Yeah.
Like running a dodgy download in a virtual machine.
Similar concept, confinement is really the practical application of these information flow models at the process level. It means strictly controlling the read and write access of a process, essentially walling it off using specific memory locations, network permissions, file system access, etc.
To limit its ability to cause damage or leak data, it shouldn't.
Exactly. It constrains its operational environment.
Okay. And then there's one more model, a really interesting one. The Chinese wall model, also known as Brewer and Nash. This isn't quite like the others, is it? It's not strictly about data sensitivity levels.
No, it's fascinatingly different. It's all about dynamically managing conflicts of interest. This is crucial in fields like consulting, finance, law firms, anywhere, handling sensitive data from competing clients.
How does it work?
It dynamically changes a user's access controls based on their previous access history within the same session or context. The core rule is something like this. Once you, the subject, access or read information belonging to, say, Company A's dataset.
Like their merger plans.
Right. Then the system automatically blocks you from accessing any sensitive information belonging to Company A's competitor, say, Company B, within that same conflict class.
Preventing potential insider trading or misuse of one client's info to benefit another.
Precisely. And the really clever part is that this wall moves based on your actions. If you first accessed Company B's data, you'd then be blocked from Company A's. It ensures that institutional separation needed to maintain professional ethics and trust.
That's quite elegant, actually. It adapts to the user's behavior.
So these models give us the blueprints, the rules of the road. But now the big question comes up. How do we actually know if a vendor's product, a firewall, an OS, whatever, actually follows these rules?
Yeah, you can't just take their marketing slick at face value, right? We need some kind of independent, verifiable proof.
Yeah.
Assurance.
Exactly. And that leads us straight into the world of system evaluation criteria. Historically, this really kicked off in a big way with the U.S. government's TCSEC, the Trusted Computer System Evaluation Criteria. You probably know it as the Orange Book.
Ah, the famous Rainbow series, the Orange Book. It was hugely influential for decades.
It was revolutionary for its time, definitely. But looking back now, it really highlights how much security architecture thinking has evolved since then.
What were its main limitations? Because it really did dominate the security conversation.
Well, the biggest limitation was its narrow scope. The Orange Book only measured confidentiality. That was its primary focus. Things like integrity and availability, they were secondary concerns at best.
So very military, keep secret focus.
Totally. And maybe even more critically, it was designed for standalone, Single box systems, think mainframes. It just didn't map well onto the complex network distributed environments that started becoming common.
Okay, but let's quickly touch on its hierarchy, those levels, D through C, B, and A. They tell a story of increasing security rigor.
They absolutely do. Level D was basically minimal protection, essentially, a system that failed evaluation or wasn't even submitted. C1, discretionary security protection, introduced discretionary access control. DAC, where owners control access.
Like basic file permissions.
Kinda. C2, controlled access protection, added stricter auditing, object reuse controls, more granular user accountability. But the major conceptual leap, the real shift, happens when you get to the B levels.
Because B introduces mandatory access control, or MD.
Exactly. And that distinction, DAT versus ME, is like the entire security architecture debate condensed, isn't it?
It really is. DAC is user-controlled, MA is system-enforced based on policy and labels.
Right. So B1 is labeled security protection. Here, data itself carries sensitivity labels like top secret, secret, and the system enforces access based on matching labels and clearances. B2, structured protection, demanded more rigor, verifying the design, addressing covert channels more thoroughly.
Getting tougher.
Yep. B3, security domains, required the system to be built around a smaller, more verifiable security core, the TCP we'll talk about later. And finally, A1, verified design, was the pinnacle. It required formal mathematical methods to prove the design met the security policy. Extremely rigorous.
And even at A1, there were other requirements beyond just the core mechanism, right?
Oh, yeah. TCSCC also mandated things they called operational assurance requirements. Stuff like trusted recovery, ensuring the system could securely reboot after a crash, and trusted facility management, dealing with secure administration roles. It was quite comprehensive for its time and focus.
But as you said, too rigid, too confidentiality focused, and not great for networks. So the Europeans came up with something else.
They did. Recognizing TCSCC's limitations, several European nations collaborated on ITSEC, the Information Technology Security Evaluation Criteria.
And how was ITSEC different? What was the step forward?
ITSEC was a pretty significant improvement. First, it was contextually aware. It could evaluate all three pillars of the CIA triad: confidentiality, integrity, and availability. That was huge.
Much more commercially relevant then.
Definitely. And critically, ITSEC separated the evaluation of a product's functionality. What security features does it have? From its assurance level, how much confidence do we have that those features work correctly and reliably?
Decoupling function from assurance. Why was that important?
It made the whole process much more flexible. You could apply it to a wider variety of products, including network systems, firewalls, databases. You could say, this firewall provides these functions and we have this level of assurance they work. TCSCC kind of bundled them together.
Okay, so ITSEC was a big step. And that separation, that broader applicability, did that sort of pave the way for what we use globally now?
Absolutely. It directly influenced the development of the current global standard. Common criteria, formerly known as ISO IEC 15408.
Common criteria. Okay, this is the one most people encounter today if they're dealing with certified products.
Right. Common criteria basically standardized how nations evaluate and certify the security of IT products, creating a common language and framework. It introduced two key concepts you need to know. First, the protection profile, PP.
What's a P?
Think of a PP as a standardized template of security requirements for a specific category of product. For example, there might be a protection profile for network firewalls or operating systems that outlines the baseline security capabilities any product in that class should possess. It's generic.
Okay, so it's the wish list for that type of product.
Sort of, yeah. Then the vendor submits their specific product for testing. That specific product becomes the target of evaluation, TOE.
The TOE. Got it. That's the thing actually being tested.
Correct. And the TOE is then evaluated against a specific PP, or sometimes against a custom set of requirements called a security target, ST, to determine how well it meets those requirements. The result is an evaluation assurance level, EAL, rating.
The ELs, right? Those go from EL1 up to EL7. Higher is better, presumably.
Generally, higher means more rigorous testing and verification, yes. EAL1 is basically just functional testing. Does it do what it says on the box? EAL2 adds structural testing. EAL3 involves methodical testing and checking. EAL4 is a really key level.
Why EAL4 specifically?
EAL4 means the product has been methodically designed, tested, and reviewed. It's often seen as a good balance between assurance and cost effort for many commercial off-the-shelf products like firewalls or some VPN gateways. You see a lot of EAL4 certifications out there.
And then it keeps going up?
Yep. EAL5 is semi-formally designed and tested. EAL6 is semi-formally verified design and tested. And EAL7 is the absolute top-tier formally verified design and tested. This involves intense mathematical analysis and proof of correctness, gold standard for rigor.
Okay, but here's the crucial insight, right? The thing people often miss, especially if they think more security is always better. You don't always need or even want EAL7, do you?
Absolutely not. This is critical. Achieving EAL7 is astronomically expensive and incredibly time-consuming. It can delay a product's release by years and massively inflate the cost.
So who actually buys EAL7 products?
Very few organizations, maybe certain high-security government or military applications. For most commercial businesses, you rarely see purchases above EAL4, maybe EAL5 in specific cases. Common operating systems often sit around EAL3 or EAL4.
So the lesson for you, the listener, is?
The lesson is, assurance costs money and time. You must always choose an EAL level that is commensurate with the actual risk and the value of the assets you're protecting. Over-engineering assurance for a non-critical system is just a waste of resources. It's about finding the right balance.
All right, we've covered the theoretical models and how we evaluate products against them. Now let's move into the actual practice, the engineering required to build secure systems.
Oh, yeah.
And there's a key perspective here, especially from NIST, that security isn't just a software feature.
Exactly. NIST's view on systems security engineering really emphasizes that security isn't something you add on, it's an emergent property. It arises from a deliberate, principled engineering process that spans everything: hardware, software, firmware, even the physical environment and human factors.
That's holistic.
Very. And this completely changes the mindset. We're moving beyond just aiming for trust, which is ultimately subjective, right? It's a belief.
Yeah.
We need to aim for trustworthiness.
Okay, what's the difference there? Trust versus trustworthiness.
Trustworthiness is the demonstrated objective ability of a system to be trusted. It's based on evidence, proof, often documented formally in something called an assurance case. It's about showing your work, proving the system behaves as expected under specific conditions.
And the fundamental framework for designing systems that can achieve that trustworthiness, that demonstrable security, it goes back to an abstract concept, doesn't it? The reference monitor concept.
It does. The reference monitor is this abstract machine, this ideal security mechanism that mediates all access requests between subjects, like users or processes, and objects, like files or data. For any real-world mechanism trying to implement this idea to be considered truly secure, it has to satisfy 4 absolutely non-negotiable criteria.
Okay, 4 essential requirements. What are they?
First, the mechanism must be non-bypassable. There can't be any way for a subject to sneak around it and access the object directly. It has to be the mandatory gateway.
Makes sense. No back doors.
Second, it must be always invoked. The protection can't be intermittent. Every single access attempt, every time, must go through the monitor. It can't be switched off or only run sometimes.
Continuous protection. Got it.
Third, it must be tamper-proof. The mechanism itself, its code, its configuration, has to be protected from unauthorized modification. If the guard can be bribed or disabled, the whole system fails. Integrity of the mechanism is key.
Okay, non-bypassable, always invoked, tamper-proof. What's the 4th one? Because you said this is often the one that trips people up in complex systems.
It is. The 4th criterion is that the mechanism must be evaluatable or verifiable. It needs to be simple enough, small enough, well-documented enough that its correctness can actually be verified by humans or through formal methods.
So complexity is the enemy here.
Absolutely. If your security mechanism is a million lines of convoluted code spread across dozens of microservices, how can you possibly be sure it's correct and doesn't have hidden flaws or bypasses? This criterion, perhaps more than any other, drives the need for the Trusted Computing Base, TCB.
Okay, let's define the TCB properly. And why is simplicity so critical for it?
The TCB is the totality of all the protection mechanisms within a computer system, including hardware, firmware, software, that are responsible for enforcing the security policy. If any component within the TCB is compromised or flawed, then the entire system security can potentially be compromised.
So it's everything security relies on.
Exactly. And the fundamental engineering principle, driven by that evaluatable requirement, is to keep the TCB as small and simple as absolutely possible. The smaller and simpler it is, the easier it becomes to analyze it rigorously, test it thoroughly, and gain high confidence, high assurance that it actually works correctly and it enforces the policy without fail.
But let me push back on that a little. In today's world, think about a massive, modern, distributed cloud environment. You've got thousands of microservices, serverless functions flying around, complex APIs, infrastructure as code constantly changing. Is keeping the TCB simple even remotely feasible anymore? Or is that principle maybe a relic of the single-server mainframe era?
That is the central, incredibly difficult challenge of modern security architecture. And DevOps, you're right, the TCB in these environments is often huge, distributed, and constantly in flux. So are we truly shrinking the TCB size? Probably not in absolute terms.
So what are we doing instead? Giving up on the principle?
No, not giving up, but adapting. We're trying to achieve the spirit of the principle through other means. We're focusing heavily on things like rigorous microsegmentation at the network level, process isolation, containerization. We're trying to ensure the integrity of TCB components, even if they're numerous, through things like secure boot, code signing, runtime integrity checks.
So breaking the problem down.
Exactly. We're trying to apply the principle granularly. We aim to verify smaller, isolated parts of the overall TCB and ensure that their interactions are strictly controlled according to policy, even if verifying the entire monolithic TCB is impossible. It's about managing complexity through compartmentalization and continuous verification, rather than just absolute simplicity. Still incredibly hard, though. Hashtag 2.2, applying architecture principles.
Okay, so within that TCB, within the system's core, we often talk about kernels. We need to clarify the difference between the system kernel and the security kernel. They sound similar, but they're not the same thing.
Good distinction to make. The system kernel is the absolute core of the operating system. It manages the fundamental resources, CPU scheduling, memory management, device drivers. It typically runs with the highest level of privilege in the system.
The boss of the OS.
Pretty much. Now, the security kernel is specifically the part of the system which might be part of the system kernel, or could involve hardware and firmware too, that is responsible for implementing the reference monitor concept we just discussed. It's the mechanism that actually enforces the access control rules, checking every request against the security policy.
So the security kernel is the TCB's enforcement arm, enforcing the reference monitor rules.
That's a good way to think about it. It's the concrete implementation of that abstract security ideal.
And we often visualize how these privilege levels work using the ring protection model.
Yeah.
It gives a nice conceptual picture.
Yeah, it's a useful abstraction. Think of it like concentric circles or layers in an onion, or maybe like the structure of a medieval castle heap.
Okay, castle keep, I like that.
Ring 0 is the innermost, most heavily fortified area, the keep itself. This is the most trusted level, where the core system kernel, maybe some firmware, resides. It has complete control.
Maximum privilege.
Maximum privilege. As you move outwards through the rings, Ring 1, Ring 2, the level of trust and privilege decreases. Ring 3 is typically the outermost ring, the least trusted level. This is where normal user programs, applications, your web browser, they all run out here.
And the whole point of the rings.
The point is architectural enforcement. Code running in an outer ring, like Ring 3, should be strictly prevented by the hardware and the kernel, Ring 0, from directly accessing or modifying resources in an inner, more privileged ring. It enforces separation and protects the core system integrity from misbehaving applications.
Makes sense. Now, stepping back to overall security strategy, there are two big philosophies people talk about constantly today. The classic defense in depth and the more modern, almost revolutionary zero-trust architecture, ZTA.
Right. Defense in depth is the traditional approach. You build layers like an onion or that castle again. You have a perimeter firewall, then maybe network intrusion detection and IDS, then host-based firewalls, maybe endpoint detection and response, EDR, application controls, data encryption, multiple layers of controls wrapped around the asset you're protecting.
The thinking being if one layer fails, the next one might catch the attacker.
Exactly. It assumes breaches will happen, so it provides multiple opportunities to stop them. But a key underlying concept in traditional defense in depth is the idea of an implicit trust zone. Once you get past the main perimeter defenses, once you're inside the network, things are often implicitly trusted to some degree.
You're on the trusted network, so you must be okay.
Kind of, yeah. And zero trust architecture, ZTA, fundamentally rejects that notion. It flips the whole idea on its head.
How so? What's the core principle of ZTA?
Zero Trust's motto is essentially, never trust, always verify. It treats trust itself as a vulnerability. It assumes that the network is always hostile, attackers are already inside, and every user, device, or application is potentially compromised until proven otherwise.
So no more implicit trust zones.
None. Access is granted based on strict authentication and authorization, but critically, this verification has to happen for every single access request dynamically based on policy. It's not just about getting through the main gate. You have to prove who you are and what you're allowed to do every time you try to open any door inside the building.
That sounds much more rigorous, but also much more complex to manage.
It definitely is. ZTA isn't a single product. It's an architectural approach. It relies on a constantly interacting set of components to make these dynamic decisions.
What are those key components?
Typically, you have a policy engine, PE. This is the brain. It makes the access decision based on the security policy and various dynamic inputs: user identity, device health, location, time of day, data sensitivity, observed behavior, threat intelligence.
A risk-based decision engine.
Exactly. Then you have a policy administrator, PA. The PA takes the decision from the PE and actually configures the communication path. It tells the enforcement points what to allow or deny. It might push rules to firewalls or gateways.
The orchestrator.
Kind of. And finally, you have the policy enforcement point, PEP. This is the component that actually sits in the data path and enforces the decision. It could be a gateway, an agent on the endpoint, a web application firewall, whatever. It monitors the connection, mediates access, and can terminate it if the policy changes or a threat is detected. They all work together continuously.
Okay, so ZTA is a continuous verification loop. Now, regardless of whether you're using defense in depth or zero trust or some hybrid, there are certain fundamental engineering principles that just always apply, right? Things like least privilege and separation of duties.
Absolutely non-negotiable foundations for any secure system. Least privilege and its close cousin need to know, which applies more to data access, dictates that any user, program, or process should be granted only the absolute minimum set of permissions, rights, or authorities necessary to perform its assigned task or function. Nothing more.
So if a service account only needs to read log files,
it should not have permissions to modify configuration files or delete user accounts. You restrict its capabilities to the bare minimum required. This massively limits the potential damage if that account or process gets compromised.
and separation of duties.
Separation of duties is about preventing any single individual from having end-to-end control over a critical process, especially one that could lead to fraud or major error. You divide the critical function into steps and require different people to execute different steps.
Like the classic example of needing one person to request a large payment and a different person to approve it.
Exactly. Or dual control for highly sensitive operations, like key recovery, where two administrators might need to be present and use their unique credentials simultaneously. It ensures that committing fraud or causing a catastrophe requires collusion, which is much harder to achieve and riskier for the perpetrators.
Makes sense. We also need to design for failure, assuming things will go wrong. That brings in redundancy and the importance of protective defaults.
Right. Redundancy is about eliminating single points of failure, SPOFs. If one component failing brings the whole system down or breaches security, that's a SPOF. So you build in redundancy, think dual power supplies, redundant network paths, or maybe a high availability pair of firewalls where one takes over instantly if the other fails.
High availability, fault tolerance.
Exactly. And protective defaults, sometimes called fail secure or secure failure, is a crucial design philosophy. It means that the system's default configuration, the state it's in right out of the box, or if a component fails, should provide maximum security and prioritize loss control.
Even if that makes it harder to use initially.
Yes. It should require a conscious, deliberate action by an authorized administrator to reduce the security posture or enable potentially risky features. The default should be deny all or most restrictive. This prevents accidental exposure due to configuration oversights. Security first, usability or performance second by default.
Okay, let's take these principles and apply them to some specific types of system architectures, starting with something fundamental. Database security. Databases are often the crown jewels, holding critical data. For their transactions to be reliable, they need to adhere to the ACD properties.
ACD is absolutely foundational for any reliable transactional database management system. ABMS, it stands for. Atomicity, consistency, isolation, and durability.
Let's break those down quickly. Atomicity.
Atomicity means transactions are all or nothing. Either the entire sequence of operations within a transaction completes successfully, or if any part fails, the entire transaction is rolled back, leaving the database unchanged. No partial updates.
Okay, consistent.
Consistency ensures that any transaction brings the database from one valid state to another valid state. It enforces all predefined rules and constraints, like ensuring account balances don't go negative where they shouldn't.
Isolation. Sounds like transactions shouldn't mess with each other.
Exactly. Isolation ensures that multiple transactions occurring concurrently don't interfere with each other's intermediate states. Each transaction should appear as if it's running in isolation from all others, preventing things like dirty reads or lost updates.
And finally, durability.
Durability guarantees that once a transaction has been successfully committed, it will persist permanently, even if the system crashes or loses power immediately afterward. The changes are written to non-volatile storage.
So ACD ensures reliable, robust transactions. But security challenges in big databases go beyond just basic access control or SQL injection, right? There are more subtle inference-based attacks. We need to talk about inference and aggregation.
Yeah, these are particularly tricky problems, especially in large data warehouses or analytics platforms where you're combining data from many sources. Aggregation is simply the process of combining multiple pieces of low sensitivity or non-sensitive data together, where the resulting collection, the aggregate, becomes sensitive.
Like combining anonymous patient records might reveal patterns about a specific small community.
Right. And inference is the attack technique used to exploit this. It's the act of deducing sensitive or confidential information by cleverly querying multiple, seemingly innocuous aggregated subsets of data and combining the results.
Can you give a classic example?
Sure. Imagine a database where you can query employee data but not individual salaries. An attacker might query, how many engineers over 50 live in zip code 90210? Let's say the answer is 1. Then they query, how many employees over 50 work in the R&D department? Again, the answer is 1. If the attacker knows that only one person in the company fits both criteria, they can now infer potentially sensitive information about that specific individual by making further queries about that group of 1, perhaps average salary for that group, effectively revealing the individual's salary.
Wow. So you deduce the specifics by cleverly combining the aggregates.
Exactly. And protecting against this requires really sophisticated access controls that aren't just based on the data itself, content dependent, but also on the user's previous queries and the context of their request, context dependent. It's incredibly difficult to implement effectively at scale without severely limiting the database's utility for legitimate analysis.
A real balancing act. Okay, let's shift to modern infrastructure. The cloud. Everyone uses it, but the shared responsibility model is still confusing for many. Let's clarify the differences between SaaS, PaaS, and IaaS.
This is absolutely crucial for anyone using cloud services. The core idea is that security responsibility is shared between the cloud provider, like AWS, Azure, Google Cloud, and you, the customer. But where that line is drawn depends heavily on the service model.
So let's start at the top with SaaS, software as a service. Think things like Gmail, Salesforce, Microsoft 365.
Right. With SaaS, the provider manages almost everything: the underlying infrastructure, the network, the operating systems, the application software itself. Your responsibility as the customer is primarily focused on managing your data, configuring access controls for your users who can see what within the application, and maybe some application-level security settings. You have the least responsibility here.
Okay, moving down to PaaS platform as a service. This might be a managed database service or an application development platform like Heroku.
With PaaS, the provider still manages the infrastructure, OS, patching, middleware. But you, the customer, are responsible for deploying and managing your own applications and data on top of that platform. So your responsibility increases. You need to secure your code, manage application dependencies, configure database security, etc.
And finally, the lowest level commonly discussed, AS infrastructure as a service, like renting virtual machines, EC2 instances, Azure VMs, or raw storage.
Here, the provider manages the physical data center, the network fabric, and the virtualization layer, the hypervisor. But everything above that, the guest operating system, patching the OS, installing middleware, deploying applications, managing data, network configurations within your virtual network, firewalls. That is all your responsibility as the customer. You have the most responsibility and the most control, but also the biggest security burden.
So responsibility clearly increases as you go from SaaS down to IS.
Definitely. You need to know exactly where that line is for any cloud service you use.
Now, focusing on Iteris, even though you, the customer, are managing the OS and applications, you are still fundamentally trusting the cloud provider for the layers below that, right? The physical security, the firmware on the servers, and critically the hypervisor that runs your VMs. What's the hidden risk in relying on the vendor for that hypervisor layer?
That is a major point of potential vulnerability. The hypervisor is this incredibly privileged piece of software that manages all the virtual machines running on a physical host. If an attacker manages to compromise the hypervisor itself, perhaps through an unpatched vulnerability or even a malicious insider at the cloud provider, they could potentially gain access to all the VMs running on that host.
Across different customers even.
Potentially, yes, in a multi-tenant environment. They could monitor network traffic between VMs, access VM memory, install persistent backdoors that are completely invisible to the guest operating systems you manage. You wouldn't see it with your OS-level security tools.
That's terrifying.
It is. It's a catastrophic failure scenario. This deep reliance on the provider's hypervisor security is why thorough vendor due diligence, understanding their security practices, and having clear contractual agreements about patching and vulnerability management are absolutely essential when using IS. You're trusting them with the foundation.
Good point. Now, people often use virtualization, VMs, and containers, like Docker, somewhat interchangeably, but they're architecturally quite different, especially in terms of isolation. Let's clarify that.
Yeah, important difference. Virtual machines, VMs, use a hypervisor to emulate hardware, allowing you to run multiple completely separate instances of full operating systems, each with its own kernel, on a single physical machine. They are relatively heavy because each VM needs its own OS, libraries, etc., but they provide strong isolation between VMs because they don't share the OS kernel.
Okay, so VMs are like separate houses on the same street.
Good analogy. Container, on the other hand, are much more lightweight. They leverage OS-level virtualization. All containers on a single host share the same host operating system kernel. A containerization engine, like Docker engine, isolates the container processes, file systems, and networking. But they're all ultimately running on that shared kernel.
So containers are more like apartments in the same building sharing the foundation and plumbing.
Excellent analogy. Containers are much faster to start, use fewer resources, and are more portable, which is great for DevOps and microservices. But the downside is weaker isolation compared to VMs. A severe vulnerability in the shared host OS kernel could potentially allow an attacker to break out of a container and affect other containers or the host itself. It's a trade-off, efficiency versus isolation strength.
Makes sense. Finally, in this section, we absolutely have to touch on industrial control systems, ICS, and operational technology, OT. These are the systems running power plants, manufacturing lines, water treatment facilities. They operate under a very different set of priorities than typical IT systems.
Dramatically different. The entire security mindset is often inverted. In traditional IT, we usually prioritize confidentiality, then integrity, then availability, CIA. In the OT world, the absolute top priorities are almost always safety and availability.
Safety first, keep the process running second.
Exactly. A security incident cannot be allowed to cause physical harm to people or the environment. An unplanned downtime of critical infrastructure or a manufacturing line can have massive financial or societal consequences. Confidentiality of the operational data is often a much lower concern compared to ensuring the physical process runs safely and continuously.
So what are the typical components we see in these environments, and why are they often so vulnerable from an IT security perspective?
Well, you have large-scale systems like SCADA, supervisory control and data acquisition, used for controlling things over wide geographical areas like power grids or pipelines. Then you have DCS, distributed control systems, which are more common for controlling processes within a single site, like a chemical plant or a factory floor.
And the devices doing the actual controlling.
Those are often PLCs, programmable logic controllers. These are ruggedized little computers that directly interact with sensors and actuators, reading temperatures, opening valves, starting motors. And here's the problem. PLCs are often designed for extreme reliability and very long life cycles. 10, 20, even 30 years is not uncommon.
So they're running ancient software.
Often, yes. They might have very limited processing power or memory, making modern cryptography or security features impossible to run. They frequently ship with default, easily guessable passwords that never get changed. And crucially, patching them is incredibly risky.
Why risky? Isn't patching good?
In IT, yes. In OT, applying a patch, even from the vendor, could introduce unexpected behavior, potentially causing the physical process to malfunction, leading to downtime, or, worse, a safety incident. You can't just reboot a power plant controller during peak hours. The validation and testing process for OT patches is extremely rigorous and often deferred for long periods, if done at all.
So if patching is often off the table or extremely delayed, what becomes the single most important security principle for protecting these ICSOT environments?
Isolation. Network segmentation. It is absolutely paramount. These critical OT networks should be, ideally, completely air-gapped from the internet and the corporate IT network. If they must be connected for data sharing, it should be through heavily controlled conduits, like unidirectional gateways or a highly secured demilitarized zone, DMZ, with strict firewall rules and monitoring. Since you often can't rely on patching the endpoints, you must rely on strong network boundaries to prevent threats from ever reaching them in the first place.
All right, let's shift gears now into the mathematical heart of security. Cryptography. This is the science and art, really, of making information completely unusable to anyone who isn't authorized to see it. We talk about the work factor, how much effort it takes to break the encryption.
Right, and the fundamental goals we're trying to achieve with cryptography can be nicely summed up with the acronym PAIN.
Okay, what does that stand for?
Privacy, which is another word for confidentiality, keeping secrets secret. Authentication, verifying identity, proving who someone is. Integrity, ensuring data hasn't been altered. And non-repudiation, proving that someone definitely sent a message or performed an action, they can't deny it later.
Privacy, authentication, integrity, non-repudiation. Got it.
And the broader field is cryptology, which includes both cryptography, making codes and ciphers, and cryptanalysis, the science of breaking them. The core components are the algorithm, the mathematical recipe or cipher, and the key, the secret value that customizes the algorithm.
And the strength heavily depends on that key, right? Specifically, the key space.
Absolutely. The key space is simply the total number of possible keys. For a key with n bits, the key space is $2. A larger key space makes brute force attacks just trying every possible key computationally infeasible.
So bigger keys are generally better. But a strong algorithm needs more than just a big key, doesn't it? It needs to resist clever attacks, even if the attacker knows the algorithm itself. Kirchhoff's principle.
Exactly. The security should rely solely on the secrecy of the key, not the secrecy of the method. And strong algorithms achieve this through two core properties that work together: confusion and diffusion. These were concepts introduced by Claude Shannon, the father of information theory.
Confusion and diffusion. Let's unpack those. What's confusion?
Confusion aims to make the relationship between the secret key and the resulting ciphertext as complex and involved as possible. Even if you have a lot of ciphertext, it should be extremely hard to figure out anything about the key. This is often achieved through substitution, replacing plaintext characters or blocks with different ciphertext characters or blocks based on the key.
Okay, obscuring the key's influence. What about diffusion?
Diffusion aims to spread the influence of each plaintext digit or block over as much of the ciphertext as possible. The idea is to dissipate any statistical patterns from the plaintext across the whole output. If you change one letter in the plaintext, it should affect many letters in the ciphertext. This is often achieved through transposition or permutation, rearranging the order of the plaintext bits or blocks.
So substitution scrambles the values, transposition scrambles the positions.
In essence, yes. And when a cipher combines confusion and diffusion effectively, it should exhibit the avalanche effect.
The avalanche effect, what does that mean?
It means that a tiny change in the input, changing just one single bit of the plaintext or one single bit of the key, should cause a drastic and unpredictable change in the output ciphertext. Ideally, about 50% of the ciphertext bits should flip.
So small input change, huge output change.
Exactly. This demonstrates strong randomization and makes it incredibly difficult for cryptanalysts to find patterns or deduce the key by observing input-output relationships.
Okay, that's for encryption. What about tools primarily focused on integrity and authentication? That brings us to hashing algorithms.
Right. Hashing is fundamental. A cryptographic hash function takes an input message of any length and produces a fixed length output, often called a hash value, message digest, or fingerprint.
And what makes a hash function cryptographically secure? What are the requirements?
Several key requirements. First, as mentioned, variable length input, fixed length output. Second, It must be easy and fast to compute the hash for any given input. Third, and absolutely critical, it must be a one-way function.
One-way meaning.
Meaning it should be computationally infeasible to find the original input message just by knowing its hash value. You can't run the function backwards. Fourth, it should be collision resistant. It should be extremely difficult to find two different input messages that produce the exact same hash output.
Got it. Easy to compute forward, impossible to reverse, hard to find collisions.
Precisely. We've moved away from older broken hash functions like MD2, MD4, MD5, and even SHA-1 is now considered weak for many uses. The modern standards are the SHA-2 family, like SHA-236, SHA-512, and now SHA-3. These are commonly used in things like digital signatures, often alongside algorithms like DSA, digital signature algorithm, hashtag 3.2 key methods, and management.
Okay, so we have encryption algorithms and hashing algorithms. Now let's look at the two main methods or types of encryption based on how keys are handled, symmetric and asymmetric. Let's start with the older, faster ones, symmetric key cryptography.
Symmetric cryptography, sometimes called secret key or shared key cryptography, uses the exact same key for both encrypting the plaintext and decrypting the ciphertext. Both the sender and receiver must have this identical secret key.
Examples would be things like DES, 3DE is AES.
Exactly. AES, Advanced Encryption Standard, is the modern workhorse. Because it uses the same key and generally simpler mathematical operations, symmetric encryption is typically much, much faster than asymmetric encryption. This makes it ideal for encrypting large amounts of data like bulk file encryption or securing communication streams.
Speed is its advantage. What's the main disadvantage?
Key management, that's the Achilles heel. Since both parties need the exact same secret key, how do you get that key securely shared between them in the first place? You can't just email it. This is the problem of out-of-band key exchange. You need a separate, secure channel just to share the key before you can even start communicating securely.
Like meeting in person or using a courier, that doesn't scale well.
Not at all, and it gets worse. If you have a group of N people who all need to communicate securely with each other pairwise, the number of unique secret keys you need to manage explodes. The formula is 9 and 1 and 1.
So for 10 people, that's $10 times 92 key equals 45 keys. For 100 people, it's nearly 5,000 keys.
Right. It becomes completely unmanageable very quickly. Also, because both parties have the same key, symmetric crypto provides confidentiality and can provide integrity using MS message authentication codes, but it inherently cannot provide true authentication or non-repudiation. If I decrypt a message with our shared key, how do I prove you sent it and not someone else who also has a key, or even that I didn't create it myself?
Good point. So the speed is great, but key distribution and lack of non-repudiation are major drawbacks. And this is exactly where asymmetric key cryptography comes in.
Precisely. Asymmetric cryptography, also known as public key cryptography, was a revolutionary breakthrough. It uses two mathematically related keys, a public key and a private key.
The key pair.
The key pair. The public key can be freely distributed to anyone. You can post it on your website, email it around. It doesn't need to be kept secret. The private key, however, must be kept absolutely secret by its owner. The magic is that data encrypted with one key can only be decrypted with the other key in the pair.
And this solves the key distribution problem.
Completely. It allows for in-band key exchange. If Alice wants to send a secure message to Bob, she just needs Bob's public key, which is public. Bob can decrypt it with his private key. No need for a prior secret exchange. This makes asymmetric systems far more scalable than symmetric ones, although they are computationally much slower.
Slower, but solves the key management nightmare. What are the main algorithms here?
The most famous is RSA, named after its inventors Rivest, Shamir, and Adelman. Its security relies on the mathematical difficulty of factoring of very large prime numbers. Another important one, especially on resource-constrained devices like mobile phones or smart cards, is ECC, elliptic curve cryptography. ECC can provide equivalent security levels to RSA, but with much smaller key sizes, making it faster and more efficient.
Okay, so asymmetric crypto uses key pairs. How do we use these pairs for the different cryptographic goals? You mentioned confidentiality.
Right. For confidentiality, if Alice wants to send a secret message to Bob, she encrypts the message using Bob's public key. Since only Bob possesses the corresponding private key, only Bob can decrypt and read the message. It's confidential.
Simple enough. What about authentication and non-repudiation? How does asymmetric crypto provide those, which symmetric couldn't?
This is where it gets really powerful. If Alice wants to prove a message came from her authentication and ensure she can't deny sending it later, non-repudiation, she uses her own private key. This is the basis of digital signatures.
Okay, walk us through the process of creating a digital signature.
It's actually a clever combination of hashing and asymmetric encryption. It's a simple two-step process for the sender, let's say Alice again. 1. Alice takes the message she wants to send and runs it through a secure hash function, like SHA-256, to create a unique, fixed-size message digest. 2. Alice then encrypts that hash digest using her own private key.
So she encrypts the hash, not the whole message.
Usually just the hash, yes.
Yeah.
Encrypting the whole message with the slow private key would be inefficient. This encrypted hash is the digital signature. She then typically sends the original message along with this digital signature.
Okay, so Bob receives the message and the signature. How does he verify it?
Bob performs 3 steps. 1. He takes the receivable message and calculates its hash using the same hash function Alice used. 2. He takes the digital signature received from Alice and decrypts it using Alice's public key. This decryption should yield the original hash digest that Alice calculated. 3. He compares the hash he calculated in step 1 with the decrypted hash from step 2.
And if they match?
If they match, Bob knows 2 things with high confidence. First, the message hasn't been tampered with since Alice signed it. Integrity, because any change to the message would produce a different hash. Second, only Alice could have created that signature because only she has her private key. Authentication and non-repudiation of origin. Alice can't deny sending it. It's incredibly elegant.
It really is. Provides integrity, authentication, and non-repudiation. But this whole system relies on trusting that Alice's public key really belongs to Alice, right? How do we manage that trust?
Now you've hit on the need for a PKI, a public key infrastructure. PKI is a whole framework of policies, procedures, hardware, software, and people needed to manage public keys and bind them securely to identities.
So what are the core components of a PKI?
The heart of a PKI is the CA, the Certificate Authority. This is a trusted third-party organization, like DigiCert, Let's Encrypt, or an internal corporate CA that issues digital certificates. A digital certificate is essentially an electronic document that binds a public key to a specific identity, a person, a server, an organization, and is digitally signed by the CA itself to guarantee its authenticity.
So CA vouches for the public key belonging to the named entity.
Exactly. Before issuing a certificate, the CA is supposed to verify the identity of the requester. This verification step is often handled by a separate entity called the RA, the Registration Authority. The RA does the legwork of checking identity documents or validating domain ownership before telling the CA it's okay to issue the certificate.
Okay, CA issues, RA verifies. What happens if a private key gets compromised or someone leaves the company? That certificate is no longer valid.
Right. For that, the CA maintains and publishes a CRL, a certificate revocation list. This is just a list of serial numbers of certificates that have been revoked before their expiration date and should no longer be trusted. Systems need to check the CRL or use a more modern online protocol like CISSP to ensure a certificate they receive is still valid.
So PKI provides the trust infrastructure for public keys. Now, where do we actually store these critical private keys securely? Especially the really important ones, like a CA's root private key.
Storing private keys securely is paramount. You don't want them just sitting in a file on a regular server. For enhanced security, we often use specialized hardware. 2 common types are TPM and HSM.
TPM, Trusted Platform Module. What's that?
A TPM is typically a small, dedicated microcontroller chip that's permanently soldered onto the motherboard of a computer, laptops, servers. It provides a secure vault for storing cryptographic keys, like disk encryption keys or platform identity keys. It can also perform some limited cryptographic functions, like generating keys or assigning data, and is often used for secure boot processes, measuring boot components, to ensure platform integrity. It's usually low cost and built-in.
Okay, built-in limited functions. How does an HSM differ?
An HSM hardware security module is a much more robust, often external, dedicated cryptographic device. HSMs are designed for high-security key generation, storage, and management, and can perform high-speed cryptographic operations, encryption, decryption, signing, much faster than a general-purpose CPU. They are typically tamper-resistant or tamper-evident, showing physical signs of tampering.
So more heavy-duty, where would you typically see HSMs used?
You find HSMs in environments that need very high assurance and performance for crypto operations. Things like protecting the root private keys of a public CA, securing database encryption keys in large enterprises, handling high volumes of SSL/TLS connections on web servers, or securing payment processing systems, like in ATMs or point-of-sale terminals. They're much more expensive and specialized than TPMs. Hashtag tag 3.3 cryptanalytic and implementation attacks.
Okay, so we have strong algorithms, key management via PKI, and secure storage with HSMs. But cryptography isn't a magic bullet. Even strong algorithms can be broken if the implementation is flawed or if the attacker has certain advantages. Let's talk about how cryptanalysts try to break codes of the different types of attacks.
Right. The classical attacks mostly focus on trying to discover the secret key. The difficulty depends heavily on how much information the attacker has access to. The most basic is the ciphertext-only attack.
What does the attacker have there?
Just what it sounds like. They only have samples of the encrypted text. They don't know the corresponding plain text. They have to try and find statistical patterns, maybe analyze letter frequencies for very simple ciphers, or just try brute forcing keys if the key space is small enough. It's the hardest type of attack, generally.
Okay, harder is the known plain text attack.
Yes. Here, the attacker has managed to obtain not just ciphertext, but also the corresponding plain text for one or more messages. This gives them much more information to work with.
How might they get that?
Maybe they know that all messages start with a standard header or end with a predictable legal disclaimer. Or maybe they intercepted both the encrypted and unencrypted versions somehow. Having those known pairs makes it significantly easier to deduce the key compared to ciphertext only.
And the most powerful type of classical attack.
That would be the chosen plaintext attack. In this scenario, the attacker doesn't just find plaintext-ciphertext pairs. They can actually choose arbitrary plaintext messages, trick the system into encrypting them with the secret key, and then observe the resulting ciphertext.
Wow, so they can feed specific inputs to see what comes out.
Exactly. This allows them to probe the algorithm's behavior very effectively. A specific type of chosen plaintext attack is differential cryptanalysis, which looks at how differences in the input plaintext relate to differences in the output ciphertext. By carefully choosing inputs with specific differences, they can sometimes deduce bits of the key. There's also the related chosen ciphertext attack, where they can choose ciphertext and get the system to decrypt it.
These sound like they require significant interaction with the target system.
They often do, yes. Now, shifting from attacks on encryption keys to attacks on hashing algorithms, we have the famous birthday attack.
The birthday attack. This isn't about finding the original message from the hash, right? It's about something else.
Correct. It doesn't break the one-way property. Instead, it targets the collision resistance property of hash functions. It exploits a probability theory concept called the birthday paradox. The surprising result that you only need 23 people in a room to have a greater than 50% chance that two of them share the same birthday.
Okay, how does that apply to hashing?
It means that it's mathematically much easier to find any two different inputs that happen to produce the same hash output, a collision, than it is to find the specific input that matches a given hash. The attack works by generating many variations of a legitimate document and many variations of a fraudulent document, hashing them all, and looking for a match between a good one and a bad one that have the same hash value.
So you could trick someone into signing a hash that applies to both a harmless contract and a malicious one.
That's the classic threat scenario, yes. Finding that collision is computationally easier than brute forcing the hash. This is why hash functions need to have a sufficiently large output size to make birthday attacks infeasible.
Okay, moving beyond purely mathematical attacks to more operational or implementation weaknesses. Replay attacks are common, where an attacker captures valid data and retransmits it later, and a very dangerous modern variant is pass the hash.
Pass the hash, PTH, is a huge problem, especially in Windows Active Directory environments that rely on older authentication protocols like NTLM, although Kerberos isn't totally immune either.
How does it work? Does the attacker need the user's actual password?
No, that's the scary part. They don't need the password itself. Instead, the attacker compromises a machine and steals the user's password hash directly from system memory, often from the LSAS, Local Security Authority Subsystem Service process, where Windows stores credentials.
They grab the stored hash, then what?
Then, the attacker uses that stolen hash directly to authenticate to other machines or services on the network as that user. The system, particularly with NTLM, accepts the hash itself as a valid proof of identity in certain challenge response scenarios. The attacker never needed to crack the password, they just passed the hash along.
Ouch. So they can move laterally across the network using these stolen hashes.
Yeah.
How do you defend against replay attacks like PTH?
Good authentication protocol should incorporate timestamps and sequence numbers into the communication packets. This allows the receiving system to detect if a message is too old, outside a valid time window, or if a sequence number has already been seen, indicating a potential replay. Kerberos does this better than NTLM. Other defenses include credential hardening, restricting local admin rights, and monitoring for suspicious lateral movement.
Okay. Another classic network attack is the man-in-the-middle, mid-M attack. This is about getting between two communicating parties.
Exactly. In a mid-term attack, the attacker positions themselves somehow on the network path between the client, say your browser, and the server, say your bank's website. They intercept the client's initial connection request.
And then?
They then establish two separate secure connections, one with the client and one with the server. The client thinks it's talking directly and securely to the server, and the server thinks it's talking directly and securely to the client. But the attacker sits in the middle, acting as an invisible proxy.
So they can see and modify everything.
Potentially, yes. They can decrypt the traffic coming from the client, read it, maybe modify it, then re-encrypt it and send it onto the server and do the same in the reverse direction. This often involves tricking the client into accepting a fraudulent SSL/TLS certificate generated by the attacker, so the browser thinks the connection is secure when it's actually being intercepted.
Classic interception. Finally, let's revisit that idea of attacking the implementation, not the math. We have side channel attacks and timing attacks. These are fascinating.
They really are, and quite devious. These attacks completely ignore the mathematical strength of the cryptographic algorithm itself. Instead, they focus on information leaked by the physical implementation of the crypto system as it operates.
Leak how?
Through various side channels. For example, attackers might monitor the device's power consumption. Different cryptographic operations or operations on different key bits might consume slightly different amounts of power. By analyzing these tiny power fluctuations over many operations, they can sometimes deduce the secret key.
Wow. What other channels?
Electromagnetic radiation emissions can also leak information, or even sound. But a very common and powerful one is timing attacks.
Measuring how long things take.
Exactly. The attacker precisely measures the time it takes for the cryptographic device to perform certain operations. If, for example, an operation takes slightly longer when processing a 1 bit in the key versus a 0 bit, perhaps due to different code paths or optimizations, the attacker can run the operation many times with different inputs and use statistical analysis of the timing variations to reveal the secret key bit by bit.
So the algorithm itself might be perfectly secure mathematically, but the way the hardware or software runs it, it leaks the secret through these side channels.
Precisely. These attacks highlight that secure cryptography isn't just about strong math. It's also about careful, constant-time programming and hardware design to avoid leaking information through these subtle physical characteristics. Flaws like Meltdown and Spectre were essentially exploiting timing side channels in modern CPU architectures.
All right, we've journeyed through models, evaluations, architectures, and deep into crypto. Now, Domain-3 brings us right back down to earth, literally, with physical security. It's easy for tech teams to forget this, but like you said earlier, perfect crypto doesn't help if someone can just walk in and steal the server.
Couldn't agree more. Physical security is absolutely foundational. It's the combination of structures, barriers, technology, people, and procedures all working together to protect physical assets and infrastructure. And often, the best approach starts way before you even put up a fence. It starts with designing the environment itself to discourage crime. This is the core idea behind CPTED.
CPTED crime prevention through environmental design. Sounds fancy, but what does it actually mean in practice?
It's about using architectural design, landscaping, lighting, and the placement of activities to influence human behavior and reduce opportunities for crime. It's often more about psychology and natural controls than just building bigger walls. CPT generally relies on 4 main overlapping strategies.
Okay, what's the first one?
Natural access control. This involves using physical features, things like clearly marked paths, fences, gates, even thorny bushes, bollards, or strategic lighting to guide people along intended routes and discourage access to unauthorized areas. It clearly delineates public space from private space.
Making it obvious where you should and shouldn't go. Makes sense. Second,
Natural surveillance. This is about designing spaces so that legitimate users feel safe and potential offenders feel like they're being watched, even if there isn't active monitoring. This means clear lines of sight, avoiding blind spots or hidden alcoves, good lighting, and placing windows overlooking walkways or parking areas. Visibility deters crime.
okay, controlling access naturally, making sure things are visible. What else?
Then you have the more psychological elements, territorial reinforcement. This uses signs, private property, landscaping, changes in pavement texture, fences, or even just flags and decorations to clearly mark a space as belonging to someone, emphasizing ownership and the private nature of the area. It creates a sense of territory that intruders feel uncomfortable crossing.
So it sends a signal. This space is cared for and defended.
Exactly, which leads directly to the fourth strategy, maintenance. A well-maintained site clean, free of graffiti, landscaping trimmed, lights working sends a strong message that the area is actively cared for and monitored by attentive staff. Conversely, a rundown, poorly maintained site, the broken windows theory, signals neglect and indifference, making it a more attractive target for crime.
So CPTED uses the environment itself as a security control. Now, just like with our system architectures, physical security needs to employ defense in depth, right? Layers again.
Absolutely essential. Physical controls should be layered, starting from the outermost perimeter of the property and becoming progressively tighter and more restrictive as you move inwards towards the most sensitive assets, like the data center core.
So maybe a perimeter fence, then security guards at the building entrance, then key card access to the office floor, then maybe biometric access to the server room itself.
Precisely. Each layer provides an independent opportunity to detect or delay an intruder. The controls should ideally be visible, acting as a deterrent, and force an attacker to overcome increasing levels of resistance and risk of detection as they penetrate deeper.
When we talk about hardening specific entry points, like doors and windows, there's a key principle about consistency of protection.
Yes, the weakest link principle applies heavily here. It's pointless investing in a super strong reinforced steel door if the surrounding wall is just flimsy drywall, or if the door frame is weak, or the hinges are exposed on the outside and can be easily removed.
The entire entry point door, frame wall, hinges, lock, must provide a roughly equivalent level of resistance.
Exactly. You need to consider specialized windows too, maybe wired glass, laminated glass, or polycarbonate, which are much harder to break than standard glass. And for controlling entry, especially preventing tailgating, where someone follows an authorized person through a door, we use devices like man-traps.
Ah, the man-trap. Explain how that works.
A man-trap is typically a small space with two sets of interlocking doors. To enter, you badge in through the first door, which closes behind you, trapping you in the small space. You then usually need to provide a second authentication factor, maybe another badge swipe, a PN, or a biometric scan, to open the second door leading into the secure area. Critically, the system ensures only one door can be opened at a time and often incorporates sensors or weight checks to ensure only one person is inside. It forces single-person entry and makes tailgating very difficult. Hashtag 4.2 data center and environmental controls.
Okay, let's zoom into the heart of the physical infrastructure for IT. The data center or server room. Its location within the building is critical. You don't want it right next to the lobby.
Definitely not. The server room should ideally be located in the core area of the facility, away from exterior walls to minimize risk from external threats like explosions or vehicle impacts. And crucially, it should not share walls with or be easily accessible from non-secure areas like public restrooms, kitchens, janitor closets, loading docks, or even public stairwells if possible. These areas often have less monitoring and could provide easier points of unauthorized access or conduits for things like water leaks.
So central location, away from shared walls with risky areas. And access control needs to be strict.
Very strict. Usually requiring at least two-factor authentication for physical entry, maybe a badge plus a PIN or biometric. Fire codes typically mandate at least 2 exit doors for safety. However, for security, only one door should be designated and used for normal daily entry and exit. The second door should be clearly marked as emergency exit only, equipped with a crash bar, panic bar for egress, and wired to an alarm system that triggers if it's opened.
Okay, location and access covered. Now, the lifeblood of the data center, power. Power problems are common and come in various disruptive flavors. We need to be clear on the terminology, especially the difference between short-term and long-term events.
Right. Let's categorize them. First, dealing with no power. A very brief, momentary loss of power is often called a fault. A complete loss of power for a prolonged period is a blackout.
False is a blip, blackout is serious outage. Got it.
Second, dealing with not enough power, low voltage. A momentary drop below the nominal voltage level, say below 80–85%, is a sag, or sometimes called a dip. If that low voltage condition persists for a longer time, it's a brownout. Brownouts can damage sensitive electronic equipment over time.
Sag dip is short, brownout is long, low voltage.
Okay.
And the opposite, too much power.
Right, too much power, high voltage. A very brief, instantaneous spike of high voltage is called a spike. If that high voltage condition lasts longer, perhaps seconds or more, it's called a surge. Both spikes and surges can fry electronics.
Spike is short, surge is long, high voltage. And there's one more related issue, inrush current.
Yes. When you first turn on certain devices, especially those with large power supplies or motors, they can draw a huge amount of current for a brief moment, much higher than their normal operating current. This is the inrush current. If you have many such devices starting up simultaneously on the same circuit, that sudden high demand can actually cause a voltage sag for other equipment on that circuit. Need to account for that in power design.
Good point. So to protect against all these sags, surges, blackouts, we rely heavily on UPS systems, uninterruptible power supply.
Absolutely essential. But there are different types of UPS, mainly standby and online.
What's the difference?
A standby UPS, sometimes called offline UPS, is the simpler, cheaper type. Under normal conditions, the equipment runs directly off the utility power. The UPS just monitors the power line. If it detects a failure, like a blackout or severe sag, it quickly switches over to its battery backup.
Quickly, but is there a delay?
Yes, there's a small but non-zero switchover delay, typically a few milliseconds. While most modern computer power supplies can handle this brief gap, some extremely sensitive equipment might still glitch or reboot. A standby UPS also offers limited protection against surges or brownouts.
Okay, so what about the online UPS?
An online UPS, or double conversion UPS, is the superior but more expensive option for critical systems. With an online UPS, the connected equipment always runs off the UPS's inverter, which is constantly being powered by the battery, which in turn is constantly being charged by the utility power.
So the utility power never directly reaches the equipment.
Correct. The power goes through a double conversion, AC to DC to charge the battery, then DC back to AC via the inverter to power the load. This means there is zero switchover delay. If the utility power fails, the battery is already engaged. It also provides excellent power conditioning, isolating the equipment from almost all power fluctuations, sags, surges, noise from the utility line.
Zero delay, better protection. Makes sense for critical loads. Okay, beyond power, the environment itself needs careful control. HVAC heating, ventilation, and air conditioning is vital for temperature and humidity.
Absolutely. Temperature extremes are obviously bad. Too hot, and components overheat and fail. Too cold, and you risk condensation issues when warmer air hits cold surfaces. But humidity control is often underestimated and just as critical.
Why is humidity such a big deal?
Because both too low and too high humidity cause serious problems. If the air is too dry, low humidity, you get a massive buildup of static electricity, ESD, electrostatic discharge. Just walking across the room can build up enough charge to zap and destroy sensitive electronic components when you touch them.
Ouch. And too high humidity.
Too high humidity leads to corrosion. Moisture condenses on circuit boards and components. Over time, this can cause metal parts to rust, or even worse, lead to a phenomenon called electromigration, where tiny metal particles, especially silver, can actually migrate across insulating surfaces under the influence of electric fields, creating unintended short circuits.
So we need Goldilocks humidity, not too low, not too high. How do we measure it?
Using a hygrometer. Data centers need sophisticated HVAC systems that not only control temperature but actively manage humidity levels, typically aiming for a specific range, often around 40–55% relative humidity, and continuously monitoring it with hygrometers.
Okay, power, temp, humidity. What about the absolute worst-case environmental disaster? Fire. Fire suppression in a data center is tricky because water and electronics don't mix well.
Exactly. A fire needs three things: the fire triangle, or tetrahedron if you include the chemical reaction, heat, oxygen, and fuel. Fire suppression works by removing one or more of these elements.
So what agents do we use instead of water sprinklers, which might be fine for a regular office but bad for servers?
While some data centers do use specialized pre-action water sprinkler systems, where water only enters the pipes when smoke is detected, reducing accidental discharge risk, gaseous suppression agents are often preferred. A common one used to be halon, but it was phased out due to environmental damage, ozone depletion. Modern replacements often include clean agents like FM200 or Novec 1230, which suppress fire chemically without damaging electronics or depleting ozone.
What about CO2, carbon dioxide? Isn't that used sometimes?
CO2 is highly effective at suppressing fire because it rapidly displaces oxygen, starving the fire. It's relatively inexpensive and leaves no residue. However, it has one massive drawback. The concentration required to extinguish a fire is also lethal to humans.
It displaces the oxygen we need to breathe.
Precisely. Therefore, CO2 suppression systems are generally only suitable for totally unattended facilities or confined spaces where personnel are not normally present. If used in an area where people might be, the system must incorporate very strict safety measures. A significant time delay mechanism after the alarm sounds but before the gas is released, extremely loud audible alarms, flashing visual warnings, and clear evacuation procedures. Safety overrides are absolutely paramount with CO2. You cannot risk discharging it while someone is still inside.
Wow. We have covered a huge amount of ground today, tracing the whole arc of Domain-3. We started with those abstract foundational security models for integrity, like Biba and Clark-Wilson, and confidentiality models like the Chinese wall.
Then we moved into how we actually evaluate systems against criteria, from the historical Orange Book, TCSEC, and ITSEC, up to the current global standard of common criteria and its EELs.
Then we dove deep into the engineering perspective, the importance of trustworthiness, the reference monitor concept, the TCB, the kernel distinctions, protection rings, and the big strategic debates like defense in depth versus zero trust.
And applied those principles to specific architectures, databases with ACID and inference issues, the cloud's shared responsibility model, VMs versus containers, and the unique challenges of IC-SOT environments with their focus on safety and availability.
Followed by a solid look at cryptography, the goals, PAIN, the core concepts like confusion and diffusion, symmetric versus asymmetric keys, hashing, digital signatures, the whole PKI infrastructure.
And importantly, how crypto can be attacked, not just mathematically, but through side channels and implementation flaws like pass the hash or timing attacks.
And finally, we grounded it all back in the physical world. CPTED for site design, layered defense, hardening entry points, and critical environmental controls for power, HVAC, and fire suppression in the data center. It's incredibly comprehensive.
It really is. And I think the overarching takeaway, the message for everyone studying this domain is this. Building genuinely secure systems isn't about finding one magic tool. It's fundamentally an ongoing engineering challenge. It involves managing complexity, understanding trade-offs between security, cost, performance, and usability, and making deliberate, informed decisions at every stage of the life cycle.
You really can't treat security as an afterthought, something you just sprinkle on at the end.
Absolutely not. It has to be woven into the fabric of the architecture itself, from the lowest level hardware design through the operating system kernel, the network protocols, the application code, right up to the physical locks on the doors and the training of the people using the system.
So given that complexity and the fact that resources are always limited, time is finite, and humans make mistakes, absolute 100% perfect security is probably impossible.
It's generally considered an unattainable ideal. There will always be residual risks, unknown vulnerabilities, limits to our certainty, so the practical goal has to be achieving adequate security.
Adequate security, meaning good enough for the specific context.
Exactly. Which brings us to the final provocative thought we want to leave you, the listener, with. Since perfection isn't feasible, you constantly need to ask, are our security engineering efforts all the money we spend on firewalls, the complexity we introduce with zero trust, the rigorous processes for key management, the physical barriers we build, are these efforts truly optimized? Are they focused on preventing and limiting potential loss in a way that is genuinely commensurate with the actual value and criticality of the assets we are trying to protect?
Or, put another way, are we spending $1 million to protect a $10 asset while leaving the crown jewels relatively exposed because we misjudged the risk or the cost benefit?
That's the crux of it. Continuously performing that risk assessment, that cost-benefit analysis of protection, and making rational, defensible decisions about where to invest limited security resources, that is the true mark of a successful security architect and engineer. It's about optimizing protection against realistic threats within realistic constraints.